Hi, I'm Steve Stach, President at Austin American Technology, and we're here today to talk about the third in our series on rose testing. And today we're going to talk about calibrating our new rose testing solvent that we've selected. So in the previous film, we have talked about the selection of a new rose testing solvent, the need for that, and how to select one. And presuming now that you've got one, here's how you would go about calibrating the new solvent. Is we want to put a known amount of sodium chloride into the solution, into the extraction solution, a known volume of that, and we're going to then calculate the amount of sodium chloride that we put in there based upon conductance change in the solution. And there is a relationship between conductance and the concentration of salt. We're going to talk about that in just a minute. But that is how we are going to do the calibration today, is we're going to put in a known amount of salt into the solution, and we're going to look for a response in conductance. And based on that response, we're going to show you how that you can calculate the amount of sodium chloride that was in there. In calibrating your new solvent, there's two things we need to check to make sure that it is going to calibrate properly. And the first thing that we need to check is basically that we're going to get a response. So we would take our meter to check this out with our new solvent and put it into a beaker of the pure solvent in its form that we receive it in. And we should be able to get a reading on the meter. Now, most modern meters today will go down to about 1 nanosiemen. Some of the really good ones will go down to 1/10 of a nanosiemen. So whatever meter you're going to use, you need to be able to read the conductance of the solvent. And some solvents just aren't conductive at all and won't be readable. So those we're going to have to check to make sure that it's readable. The second item that we need to make sure we have is we need to have a linear response. And what I mean by that is as we add more salt to the solution, we want to have a linear response. Now, if we use resistance and look at resistance as a function of concentration, we won't get a linear response. In fact, if you look at the graph here, you can see that you get a nonlinear response with resistance. On the other hand, using conductance, we typically do get a linear response with regard to concentration of the ions. So we will use conductance. So going into the laboratory, if we make up a standard salt solution to test our new solvent and see that it does have a linear response. And what we're going to do is go in the lab, take our solvent, we're going to add in a stepwise fashion a known amount of sodium chloride solution, and we're going to measure the response we get in conductance. And we're going to plot those steps in a graph, and we're going to look at the graph and make sure that that graph and that response is linear, at least in the area that we're going to be operating in. So if we're going to be operating in the 1 nanosiemen to 10,000 nanosiemen range, we want to make sure that that area, that range, that we have good linearity of that graph. That will give us a predictable result and a very highly accurate result as long as we have that linearity. So now we've collected the data in the lab. Let's look at some data for just a second. So this data here is the data that we collected for isopropyl alcohol and water. And if you look at the red line, you'll see that that is our typical 75-25 water that's called out in the IPC and the military specifications. The IPC has a tolerance on the amount of water and alcohol that we can have of plus or minus 5%, ranging from 70 to 80%. In the graph here, we can see that if that is exceeded, that we get significant error introduced and that the line shifts upwards. In the case here for the green line, we've evaporated too much alcohol and the line shifted upward. In the case here, we have added too much water and it shifted downward. Now, we're not subject to this when we have pure solvent systems like pure alcohol or pure water. And if you look on the far left-hand side of the graph also, you can see where we've plotted DI water and its response to sodium chloride being added to it as well. And it is linear in this range as well. So if we look at some other solvents, not all solvents are linear like this. And here's an example of another solvent that we've tested, and we've got a nonlinear response. So if we wanted to use this solvent, we would have to use it only in a very short region where it is linear. not in the total area here that we're looking at where it's nonlinear, because we would not get a predictable result based on the math that we're using. Before we get started on calibration, I think it's important to spend a little bit of time talking about the units of the ROSE test and how that relates to the calibration. So when we talk about the units of the ROSE test, the units are sodium chloride equivalent per square centimeter. And what we mean by that is that in our test, what we do is we put the circuit board into a solution, our extraction solution, and the ions begin to dissolve off. We don't know exactly what ions they are. They could be calcium, potassium, sodium, bromine, chlorine, fluorine, any of those, or any anion or cation from the flux itself. But we don't know what ions are there, so what we're going to do is we're going to look at the change in resistance or change in conductance, in this case, and we're going to make an equivalent amount of change with sodium chloride. So that if we imagined that all the ions that came off of the board were sodium chloride instead of these other ions we just talked about, then how much sodium chloride would it take to give the same amount of conductance change? That would be what we call the equivalent sodium chloride concentration. So when we have the units, we're talking that we understand that we're not getting an identification of all the ions that are coming off, but we're getting a result that we can match with sodium chloride in a known quantity, an equivalent amount of sodium chloride to get that amount of change. So having said that, it's just important to understand that as we move forward in our calibration, that's what we're actually measuring is the equivalent amount of sodium chloride, not the ions that are coming off the board themselves. So now that you have your calibration standard, what you're going to want to do is you're going to want to take a certain known quantity, and you can measure that by various methods. We prefer to use a syringe generally. And the solution that we've made up is going to represent 10,000 micrograms of sodium chloride per milliliter that we pull out into the syringe. When you fill your syringe, be careful not to get any air bubbles in there. If you do, bring them to the top, expel them from the volume, and make sure you've got a good solid measurement of the volume that you're measuring out for the test. So here we inject the sodium chloride, and you can see that we are now getting a response on the sodium chloride, and it is ramping up, and it's measuring that increase in conductance that will stabilize and plateau out and give us a reading. And that reading, that change in conductance, is what we're going to use in our calculation to determine the amount of sodium chloride that's present. In this case, the machine's going to do that calculation for us. And on the final screen here, we can see that we had a known amount. We've injected 50,000 micrograms, and we've got out approximately 50,000 micrograms. And in looking at the data a little bit closer, what we're going to see on the graph is that we can also discern some important things from this. The slope of the line that we have here basically is going to give us our constant that we're going to need for a given solvent. So if that slope is high or low, it's going to give us a higher constant or a lower constant. That's where the constant comes from, is the slope of that line in this data set. The intercept of the y-axis is going to tell us what our offset is. In other words, what our CO2 absorption is and what our background absorption is. So where it intercepts that line, we're going to be able to tell the background amount that we have. So this really gives us a lot of data. It gives us the slope of the line, which is the constant we need. It gives us the background information. It also shows that we're linear in the ranges of calibration that we're going to be operating with. Now we have truly defined and understood the new solvent system, and we have calibrated the new solvent system, and we can do this repeated and with great accuracy over and over again. So that's how you do it, and that's how you do the calibration. Thank you again for your attention and for watching the series on ROSE testing. We thank you very much here at AAT, and if you'd like to contact us for further information, please do so at the addresses and websites listed here. Thank you again.